Molecular physics is the study of the physical properties of molecules, the chemical bonds between atoms, and also the molecular dynamics. Its most essential experimental techniques are the various types of spectroscopy. Scattering is also used. The field is closely related to atomic physics and overlaps greatly with theoretical chemistry, physical chemistry, and chemical physics. Additionally to the electronic excitations state which are known from atoms, molecules are able to rotate and to vibrate. This rotation and vibration are quantized, which means that they are discrete energy levels. The smallest energy difference exists between different rotation states, therefore pure rotational spectra are in the far infrared region of the electromagnetic spectrum, vibrational spectra in the near-infrared, and spectra resulting from electronic translation, and mostly in the visible and ultraviolet region. From measuring rotation and vibration spectra, properties of molecules like the distance between the nuclei can be calculated. Molecular modeling involves all theoretical methods and computational techniques used to model the behavior of molecules. The techniques are used in the areas of computational chemistry, medicine design, computational biology, and material science for studying molecular systems, range from small chemical systems to large biological molecules and material assemblies. The simple calculations can be performed by hand, but inevitable computers are required to perform molecular modeling of any reasonable size system. The common fire of molecular modeling techniques is the atomic level description of the molecular system. This may include 13 atoms and the smallest individual unit, or explicitates modeling electronics of each atom. Molecular mechanics is one aspect of molecular modeling, as it refers to use of classical mechanics to describe the physical basics behind the models. Molecular models typically describe atoms as point charges with an associated mass. The interactions between neighbors atoms are described by spring-like interaction and van der Waals forces. The Lennard-Jones potential is commonly used to describe van der Waals forces. The electrostatic interaction are computed according to Coulomb's law. Atoms are assigned coordinates in Descartes space or in international coordinates, and can also be assigned velocities in dynamical simulations. The atomic velocities are related to the temperature of the system, which are of the macroscopic quantity. The collective mathematical expression is known as a potential function and is related to the system internal energy and thermodynamic quantity equal to the sum of potential and kinetic energies. Methods which minimize the potential energy are known as energy minimization techniques, while methods that model the behavior of the system with propagation of time are known as molecular dynamics. This function, referred as a potential function, computes the molecular potential energy as a sum of energy terms that describe the deviation of bond lengths, bond angle, and torsion angles away from equilibrium values. In addition to the terms, for non-bonded pairs of atoms describe van der Waals and electrostatic interaction. The set of parameters consisting of equilibrium, bond lengths, bond angles, partial charge values for constant and van der Waals parameters are collectively known as a force field. Different implementation of molecular mechanics use different mathematical expression and different parameters for the potential function. The common force field being in use today have been developed by using high-level quantum calculations. The techniques known as energy minimized is used to find position of zero gradient for all atoms and other words a local energy minimum. Lower energy states are more stable and are commonly investigated because of their role in chemical and biological processes. A molecular dynamics simulation, on the other hand, computes the behavior of a system as a function of time. It involves solving Newton's law of motion, principally the second law. Integration of Newton's law of motion using different integration algorithms leads to atomic traction in space and time. The force on an atom is defined as the negative gradient of the potential energy function.